Section 5.1 is estimating with finite sums. So let's first talk about a problem that you're familiar with. If I want to find the distance that I have traveled, if I'm going 60 miles per hour for 3 hours. It's a pretty simple problem. 60 miles per hour for 3 hours gives me 180 miles. What we're doing, we're finding distance using velocity and time, is actually finding area under a curve. So if I graph my velocity here and my time here, 1 hour, 2 hours, 3 hours, and my velocity, 10, 20, 30, 40, 50, 60 miles per hour, when I'm going 60 miles an hour at a constant rate for 3 hours, the area of this rectangle, which is miles per hour times hours, miles per hour times hours, will give me how many miles I've gone. We can do the same thing if my velocity is increasing in a linear fashion. So if I start at 0 miles per hour and go up to 60 miles per hour, I can find the area of this triangle, and that will tell me how many miles I've traveled. The difficulty comes in when my velocity maybe isn't a constant. How am I going to find the area from 0 to 3 if this curve is constantly changing in a nonlinear fashion? So that's what we're going to be working on today. It's still area under the curve. We're just going to find it by using finite sums. This says example, finding distance traveled when velocity varies. So a particle starts at x equals 0 and moves along the x-axis with a velocity v of t equals t squared. That's a changing velocity for any time greater than or equal to 0. Where is the particle? In other words, how far has it traveled? Since it starts at 0, where is the particle at t equals 3? So here's what we're going to do to solve this method. We're going to graph v and partition the time interval into subintervals of length delta t. If we use delta t equals 1/4, let's show this on the graph, then my intervals make up 12 subintervals. Each one has a distance or a width of 1/4. The area of each rectangle approximate the distance traveled. So adding all of these distances together gives us an approximation for the total area under the curve. So if I look at this rectangle up here, if I look at the midpoint and find a value for that using my function t squared and multiply it by 1/4, I will get the area of this rectangle. If I do it again for every other rectangle, I will have a pretty good approximation. So let's look at this. So again, my graph looks something like this. I'm going from 0 to 3, and I'm dividing this into 12 pieces. Every unit is going to be divided into distances of 1/4. So each rectangle is going to be 1/4 times some x value. Let's start with our first one. If my first subinterval goes from 0 to 1/4, my midpoint is 1/8, and I'm going to square it because my function is t squared. My next midpoint, let me expand this a little bit. So if I divide this into four pieces, each piece is 1/4, my midpoints will be 1/8, 3/8, 5/8, and 7/8, and then the same for my next one. So each of these, to find my height, I'm going to take the square of it, and my width is 1/4. So 1/4 of 3/8 squared for my second rectangle. Excuse me. 1/4 of 5/8 squared for my third rectangle. I hope that you can see here that 1/4 is a constant. My subintervals, or my rectangles, have all the same width. So I can rewrite it like this. 1/8 squared plus 3/8 squared plus 5/8 squared. And I'm going to keep going all the way up to my last subinterval, which is 1/8 shy of 3, which would be 23/8 squared. If I put those in my calculator and multiply them all up, I'm going to get 8.98. What was my units? I didn't have units. Okay, so miles, feet, whatever the units would be. So that's my total area under this curve. And it's a pretty good approximation. We call this rectangular approximation method, or RAM for short. All right, there are 3 kinds of RAMs we can do. LRAM, L-R-A-M, MRAM, and RRAM. So each of these has been divided into 1, 2, 3, 4, 5, 6 subintervals from 0 to 3. My left uses the side at the left of each rectangle. So I'd be using these points, and I would go up to 2.5 for my left. My midpoint takes the midpoint of each of my rectangles. So I'd have to divide each of these in half to get my mid-RAM. My right RAM starts on the right side of each rectangle. I don't use 0, and I go all the way up to 3. Now, in most cases, your mid-RAM is going to be the most accurate. We can see here that with the left RAM, when the function is increasing, this would be an underestimate. This one is almost equal. The part that I take and the part that I miss is almost the same, but not quite. My right RAM, in this case, is an overestimate. We'll talk a little bit more about that later. Left RAM is not always an underestimate. If my function was concave down, and I took the left side of each rectangle, then it would be an underestimate. So be careful. It varies from case to case, but most of the time we can tell whether our rectangular approximation method gives us an underestimate or an overestimate. Okay, so let's try another one. Let's say I want the area under the curve x squared sine x from 0 to 3 using 6 subintervals. And I'm going to use left RAM. So if you want to get your calculator out, that would be helpful. If you want to look at this function, it looks something like this. And I'm going up to 3. I'm using 6 subintervals, so that means that I'm going to separate everything at halves. And I want the left RAM, so I'm going to use 0 for my first one, 1/2 for my second, 1 for my third, 1.5 for my fourth, 2 will be the height of my fifth rectangle, 2.5 will be the height of my last rectangle. I will not use the value at 3. All right, each one of my rectangles has a delta T of 1/2. That's the width. So I'm going to take 1/2 times my first rectangle starts at 0. So f of 0 plus f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2. Remember, I'm not using 3 because I'm not doing another rectangle after 3. All right, so calculators, if you set up your function in a table, you can get these values pretty quickly. If you don't know how to do that, be sure to ask me when you get to class. But set up a table for y equals x squared sine x. Go to the table and plug in 0. We should get 0. If I plug in 1/2, I get 0.11986. The next value, 1, I will get 0.84147. Continue on, plus 2.2444 plus 3.6372, I'm running out of room, plus 3.7405. If I add those up and multiply by 1/2, I get 5.291715. And that is my area under this curve from 0 to 3 with an approximation. Screen's jumping around today. Okay? So that's all we're going to talk about in the video. We're going to do one more problem with volumes when we get together, but that's it for the notes.